Damn, fan.
I don't know if it's on a delay.
It's on.
Okay. Okay, so we're back. And we're going to start right up with Lecture 7. And I'm just going to hand it on over to our buddy Alex.
Okay, thanks very much. So we've been looking at, what were we doing last week? We were doing tree proofs. So we were introducing tree proofs for the first time. So it's another method for like testing formulas and arguments in propositional logic. It's just like truth tables that we had before. It does all the same tests. It's just that it's better for the purposes of, if we've got a formula with lots of variables in it, with lots of propositional letters, then the amount of rows that we have to write in our truth table becomes very cumbersome very, very quickly. It's to you have to double the amount of rows every time you have another propositional variable in there. So as soon as we have 3 or 4, we're writing out 16, 32, 64 rows. It starts to become very, very difficult. So while truth tables are good as a way of getting a handle on the basics, if we want to do anything more complicated than that, we need a more sort of versatile method. What we're going to do today is continue looking at so there were 2 rules for each of the connectives, and we've got 5 connectives. That's not, and, or, if then, and if and only if. So we've got 2 rules for each of the binary ones and 1 rule for the negation. We've already done the negation rule, and I think we did the conjunction and disjunction rules. So we're going to do the if-then rule and the if and only if rule today. And then what I'm going to do is show you an interesting property about these methods of proof that we've got, which is basically that it captures the notion of validity that we're looking at. And what that would mean is I'll show you that these methods of proof are both sound and complete. So these are interesting logical properties, very, very useful logical properties. I'll go into a bit more detail about that. If we've got time, I'll talk a bit more about material implication and the so-called paradoxes and some of the different ways that philosophers have come up with for kind of getting around them, and what interesting kind of avenues of philosophy that gets us into. So let's just start off by recapping what we were doing. So hopefully we've got this slide open so everyone can see that slide, I take it.
Yep.
Yeah, okay, good. So we've got, as it says, so we've got a method of tree proofs. It's an alternative method to demonstrate that an argument form is valid, or that a single formula is a tautology or contingent or whatever. It's exactly the same tests. So at the top of the tree, we write out all the premises and the negation of the conclusion. It's the main thing you've got to remember when you're doing this, is that if you just write out the argument with the premises and the conclusion, then it's going to go wrong, and you're not going to, the test that you do isn't going to give you the result that you want. You have to write the negation of the conclusion. Yeah, so I'll go into that in a bit. Yeah. Then we apply the rules. So I've given you half of the rules already, and we'll go through the rest of them in a minute. And then what we do when we apply the rules, we're unpacking all of the complex formulas, all of the molecules. We're unpacking them down into their atomic parts. And then once we've finished unpacking them, we've got lists of atomic propositions, either P or its negation, not P, that type of atomic parts. And we call each of those strings or lists of atomic formulas or their negations, we call them branches. So we might have, well, we'll see in a minute, we'll have ones that have lots of different branches. And what you do is you look along those branches to see whether a formula appears along with its negation. If it does, then we say that that branch is inconsistent. So inconsistent just means exactly that it's got a formula and its negation. So it's like the general everyday sense of inconsistency. Like if someone says, I really like ice cream, and then 2 minutes later they say, I really hate ice cream. You're saying, well, you're being inconsistent, dude. You said that you liked ice cream, now you're saying that you don't, right? They're saying P and they're saying not P straight away afterwards. So if a set or a string of formulas is inconsistent, it means the same thing. It means that it's got P and it's got not P. It's got something and its direct negation in there. Now, if we find that every branch, after we've unpacked all of the molecules, if we go through each branch and we find that all of them close, then we say that the argument is valid. That's because there's no way that we can make the premises true and the negation of the conclusion true. That means that there's no way that the premises can be true and the unnegated conclusion false. So that's what we're testing for. We're trying to find whether or not there's a branch that doesn't close, if there's an open branch. An open branch means that the argument is invalid. So if all of the branches close, the argument is valid. Okay, so it's strictly speaking, this is a test for invalidity, and it fails if all of the branches close.
Yes.
Okay,
yes.
so
we got that.
Yeah, it's kind of tricky to keep all of these like concepts of like what's closing, opening, valid, invalid, test failing or passing. But the more examples you do, the more you go over this content, the more straightforward it becomes. So I'll go through it for now. And any questions at any point, just interrupt me. Don't be rude. Don't feel
okay,
rude.
so I've got one already. I just want to double check. I'm thinking about it. Okay, so the way I think about this is, it's like the trees just immediately sort of give you a counterexample. And so you want to check that counterexample. Yeah,
I guess that's right. So if so we'll see in a minute, but to pull the rabbit out of the hat now, what we're going to find is like if you wrote out your truth table, what you'd be looking for after you'd finished writing that all out was a row on which the premises were true and the conclusion was false. If you've got hundreds and hundreds of rows, you could be there all day, even after you've written it out, then trying to find one that has true premises and a false conclusion. And what this test is going to do is it's just going to find that for you. So it's like a sniffer dog. It just goes straight to that line of the truth table.
That was the sort of thing I didn't fully appreciate when you talk about following the tree. What you're doing is you're following all the truth options in all the possibilities. Instead of putting it in a big table, you're starting to find all the truth options and then finding if those then end up with a false at the end.
Yeah, that's right. Well, we're trying to find if there is a consistent way of having, like, if the premises and the negation of the conclusion can be consistently held together.
Yeah.
And if they can, then the argument's invalid.
Yeah.
Okay, that makes sense.
Let's crack on. Good. All right, good. So, we've had these two rules so far. So the rules for disjunction over on this side. So if it's an unnegated disjunction, then we write two branches, right? It's splits, essentially. So we have a branch going on the left-hand side where we just put whatever the left disjunct is. And on the right-hand side, we have another branch, and then we put whatever the right. So did I say right? Yeah, on the right-hand side, we put whatever on the whatever the right disjunct is. On the other hand, if our disjunction is negated, then we just have a single branch, and underneath that we write not whatever's on the left-hand side, and underneath that we put not whatever's on the right-hand side. So intuitively, think about it. If you've got A or B, then what you need to do is consider one case where A is true and another case where B is true. So if you've got two separate branches going on, you know you've covered all the ways in which this thing could be true.
Exactly. That's the key thing I think we need to work out. It's all the ways it could be true, and then you end up with the branches for all the cases it can be true, and then that gives you your truth because you're searching for truth all the time.
Right, and just writing them like that.
And therefore, the reason it's better on the table, of course, is you don't then have to consider all the not truth cases, and that's why it's so much easier.
Exactly. Yes.
Okay, good. So if we've got our negated disjunction, then it's saying it's not A or B. It's neither A nor B. So we know that it's not A and it's not B. So we put both of them underneath the negated disjunction. And then the rules for conjunction are, like I said before, kind of like a mirror image of the rules for disjunction. So if conjunction is unnegated, if it says A and B, then it sounds fairly intuitive. I think we just have one branch underneath which we write both A and B. And then if it's negated, it's saying it's not A and B. So we know that if the case is not A, then that's certainly going to be not A and B. And if it's not B, that's also going to be not A and B. So all we need to do is consider the cases where not A is true and all the other cases where not B is true. So if we do that, we know we've covered all the cases. So I think in this one, or maybe in the next one, I'll actually be directly linking back trees to truth tables. So you'll see it'll make sense, hopefully.
So if you practice truth tables, that link is just obvious. So
yes.
If you just do a million truth tables, it'll just be so obvious you won't even need to think about it anymore.
It's a search for truth, basically. Seems to me.
So I think the thing to remember about this is that none of this is hard, right? None of this is hard. It might seem like hard when you first listen to it or come across these things, but it's no harder than arithmetic. If the first time you learned arithmetic was when you were 35, and someone starts going, you've got plus and minus, and the rule for subtraction is blah blah blah, you'd probably find it quite difficult. But because we do it from such an early age, it's really very, very easy. And if you think about it, in arithmetic, you've got 4 operators, you've got equations that give you values for each of the things that you just intuitively understand that there's correct ways to write things. You can't write times minus 3. That doesn't. Well, I suppose you could do that,
but you can do actually.
Yeah. All right, but you know what I mean. Pluck some like a random string of symbols together. It's probably not going to make some proper arithmetic formula. But you don't say that to a 5-year-old or whatever when they're first learning. You probably would do. You probably would approach it like that if you were teaching it to a 35-year-old who'd never learned it before, and you just give it to them the proper way as an adult. But really, the content it would be no different. And here we're doing exactly the same thing. Propositional logic is as complex as arithmetic. It's probably less complex than arithmetic, actually. So if it sounds like it's complicated, just remember to yourself, it's not. It really isn't. Once you get it all in your head, it's very, very easy. It starts to become a little bit more complicated when we're doing first-order logic in a little bit, but even that, we're building upon a solid foundation. So if you get this, you only have to add on a few more houses to your street in order to get first-order logic as well.
Okay, so let's move on.
Okay, good. So let's do an example that uses the rules that we've got. So here's an argument. It says first premise is P or Q and not P or R. Second premise, not R. Conclusion, therefore, Q. So what we do is we write out the premises underneath each other like this. We write out the first premise. Underneath that, we write out the second premise. And underneath that, we write out the negation of the conclusion. Remember, if you write the conclusion, you're going to be testing to see whether the the truth of the premises is consistent with the truth of the conclusion, which isn't going to be a good test to see whether it's valid or not. Now, what we want to do is see whether or not the premises can be true and the conclusion false. Yep. That's why we're doing this, okay? So always write out the premises along with the negation of the conclusion. So we've written it out. Now what we need to do is unpack all of the molecules. There's only one molecule here, but it's complex. So let's start unpacking it. First thing we have to do is, because the and is the conjunction in the middle is the main connective, that's the thing we need to unpack first. And what we do is we put whatever's on the left-hand side underneath, like because it's the and unnegated and rule, we're just going to put what's on the left-hand side and what's on the right-hand side both underneath it. So this is let's just quickly go back so everyone's clear about it. We're using this rule here, right?
Yeah. Yeah.
And what A on this side and B are these.
Yep.
And these, right? That's A and B. So that's why we're writing them down underneath here.
Yep.
Okay, good. So we unpack that first thing. Now what we need to do is unpack each of these. So let's unpack this P or Q. So we know our unnegated disjunction rule means that you write a branch on the left and put whatever's on the left-hand side, and a branch on the right and put whatever's on the right-hand side. So we've unpacked that. We can already see here that we've got a sort of proto-branch, but we know that there's a contradiction, right? These two contradict one another, so we can already close that. We don't need to add anything more to that branch. Obviously, if there's already a contradiction, nothing else that we add to it is going to change whether or not there's a contradiction in it. So we don't need to add anything further to that, so we can close it, which is nice. We've still got one molecule we haven't unpacked. Like if you were doing this as homework, I would be recommending to you that you tick off each of the molecules when you unpack them, or put a line through them or something so that you know you've done it, just so that you don't end up missing one in an exam or doing one twice or something. Although doing one twice wouldn't matter. As long as if you missed one, it would mess things up. Anyway, okay, so we need to unpack this. So it's another unnegated disjunction. So we put what's on the left-hand side down here in the left branch, and whatever's on the right-hand side in the right-hand branch. Now we've actually got a contradiction there. We've also got R down here and not R at the top. Oh yeah, I suppose that's a separate branch. So sorry, I'm confusing myself. So yeah, obviously this branch, the one I've highlighted, that's got a contradiction in it, right, which is P and not P. So we can close that branch. And now if we consider this other branch that goes from not R to R, well, that's got a contradiction in it too. And so that closes. So we've unpacked all of the things, or all of the molecules into their atoms, and we've checked all 3 branches that it's made, and all of them close.
Sorry, I've just slightly. Where have you unpacked the P or Q bit? I saw you did the not Q and the R. Where did you unpack the P or the Q?
here we go. I've rewound to it, so I'm highlighting it now. This is me unpacking it.
Oh, and you put it underneath, right? Okay, you put it underneath. This is your notation of trees. It's slightly uncomfortable, but okay, right. So that's the point of unpacking it. Okay.
Yeah. So I mean,
Right.
like what we did, we start off with this, and then anything I unpack is it's a branch technically. It's a single branch, and then anything else I unpack, just keep writing underneath what you've already put. So I mean, it's systematic. It's systematic.
I suppose so. Okay.
I may have missed this. Why is that under the negative, the not R? Why is the not Q there? Where does that come from?
Okay,
That
so
to negate the conclusion, right? Because you got to put that in there, right? Because that's what you're trying to do. Okay, that's good. All right, I'm okay.
Go back to where you were now.
I think that you can't say that enough, really, because the conclusion was Q, and you have to put not Q down as the thing.
You're trying to find out if it's a valid statement. That's right. Okay.
Well, yeah. So we're actually trying to find out whether it's invalid, and so strictly speaking, I mean, what you said is right. Really, we all know what you mean, but really strictly speaking, the test is to see whether it's invalid.
Right.
And if it passes, that means if there's an open branch, then it is invalid. If it fails, that means if all of the branches close, then it's valid. Okay, so we'll just do this. So we've already done this. We saw that basically all you do is you write out your argument and then get rid of the molecules until you've only got atoms. And then if you've only got atoms, then you can check those branches to see whether or not the same atom appears with its negation. And if it does, then you can close the branch. That's it. And then that's all I've done here. I've just applied the rules that I've already shown you and drawn it out like this. So it's just a series of mechanical tasks. The more familiar you become with them, the easier this is to do. There's no magic here. You don't have to think. All you have to do, if you have all of the rules written down on a piece of paper next to you, you could, at every single step, you could just look and it would tell you what to do. You wouldn't have to think about it. A machine literally could do this.
Yeah, that's the thing that confused me was when you unpack something like that P or the Q, you actually apply it to the thing underneath it, and then similarly when you unpack the not P or R there, you actually unpack the things beneath it. So it's this, you always unpack the thing beneath it from the rule above it. If that you would do it.
So I think what you're trying to say is when you unpack a molecule, what you do is you, underneath your entire existing tree already, you write the results of your unpacking.
Yes, I think that'd be compatible with what I said. Yes.
Yes. Okay. Good. All right. Great. So let's. So basically, we've shown that every branch closes, and that means that the argument is valid, because there's no way that the premises can all be true along with the negation of the conclusion. What that means is if the premises are true, the conclusion not negated, the actual conclusion has to be false. So if the premises are true, the conclusion is false. That's just what it means for it to be valid. Okay, good. So now let's introduce some new rules. We haven't seen these rules already. Get it. Hold on to your seats. So they're always really the same sort of rules. So this is the rules for implication, if-then. So if we've got an unnegated if A, then B, then what we do underneath it is we write on the left-hand side, we write not whatever the antecedent is, so in this case not A, and then on the right-hand side we just write whatever the consequent is, so in this case B. Now, if you think about it, if we went back to our truth table for if-then, you might just take my word for it, but if the antecedent is false, then the whole conditional is true, and if the consequent is true, then the whole conditional is true. And that's because the only way that the conditional can be false is if the antecedent is true and the consequent is false. So all you have to do is specify that either one of those things isn't the case.
Yeah, you could really do with the
true conditional is true.
You could really do with the fact that the component of that is not P or B, really, couldn't you? But no.
Yeah, so I think it might come up in a moment.
Right.
But I'm doing it as a PDF, so I don't have the slides down the side.
Okay.
Anyway, so we've got the negated conditional rule saying, not if A then B. Well, that is saying that the conditional is false, essentially, and that means that the antecedent is true and the consequent is false. So if we write A underneath it and not B, then we know that we've ensured that this whole thing, which says not A, if A then B, we know that that's going to be true. So that's why we write underneath it A and not B. So I think with the rules with conjunction and disjunction are very easy because they just spell out what we mean by or and in a very, very straightforward way. Because conditionals in propositional logic are a bit unintuitive, I've spent a bit more time trying to just say why we write them down this way. But on the other hand, they're just a bunch of mechanical rules, and you just do what it says here, and you pass the test kind of thing. So yeah, there's two things to this. One is it's not very intuitive. The second one is just do it anyway because it's just a bunch of rules, and that's it. That's all logic is. Right. Okay, yeah, why? So here we go. I do, in fact, give you the truth table here. So on the one hand, not A, well, that's all these rows of the truth table where A is false. Well, in both of the rows where A is false, the conditional as a whole is true. Right? And in both rows where the consequent is true, the first one and the third one, well, that also makes the conditional true. So all we have to do to specify that the conditional is true is just say it's either these two bottom rows or the first row and the third row. That's it. And we've covered all the cases where it's true. That's why this works. And then all we need to do for this one is just corresponds to this second row of the truth table. So already I think now you can just see there is going to be a direct link between what these rules are doing and what the truth tables are doing. They're really just saying the same thing in different ways.
The branches are the rows.
Well, in this case, this branch does correspond to a single row. In this previous case, there isn't a one-to-one relation between the branches and the rows. Yes. This branch covers two rows, and this branch covers two rows, and one of them overlaps with this one. So it's not quite right to say that they are exactly the same as the rows, but there is a relationship between the rules and the properties of the truth tables, which is they're mapping the same thing. Yep. Okay, good. Good. Sorry, I don't mean to be pedantic, but in a sense, you have to be pedantic.
Yeah. No, it's important.
Yep. We like your pedanticism.
Good. That's why I like teaching logic, is because I'm quite pedantic anyway, and it's just like a thing
is that
can be
why
ultra
you're
pedantic.
Pedantic logician girlfriend? You couldn't. Another rule of logic is you have to have a logician. Jesus Christ, a logician for a girlfriend or partner.
So are you pedantic because you study logic, or are you logic because you're pedantic?
I do logic because I'm pedantic, definitely.
Without a doubt.
And no, it would be far better to have a girlfriend who didn't realise.
You can't confuse her.
Yeah. Well, it's not because she wouldn't realise it. It's because she could cajole you into a better mood.
No, but she's actually, I would say, better at this than I am. So I don't get anything past her for sure. She's got naturally very, very sharp. So I don't get away with anything. Anyway, my personal life has nothing to do with this. All right, good. Let's just carry on with this. Okay, good. So let's use this conditional rule. So we've got an argument: if P, then Q. P, therefore Q. Well, let's write it out. We write out the premises, two premises, and the negation of the conclusion. I feel like I should do this in a kind of pantomime way. Write out the premises and then you will shout negation of the conclusion.
Yeah, we know that. Well, I think we know this one now. It's an old hat for us, I think now.
Yeah. All right. Good. So we unpack the molecules. Only one molecule. What we do, we think about our unnegated conditional rule. So we write out two branches: one that negates the antecedent, and then the second one that writes out the consequent. So this is me writing that out and applying it to this. So I write out not P on the left-hand side and Q on the right-hand side. Then I've unpacked all of the molecules, only one. So that means now I just check the branches to see whether they're consistent or not. On this side, there's a contradiction. So we close it. On this side, there's a contradiction. So we close it. Therefore, no surprise, this argument is valid. It's no surprise because I think everyone would probably recognize this as the argument form known as modus ponens. So I mean, not a big surprise that that's valid, but at least we can apply and check and make sure that it is valid. I mean, really, if someone is giving you an argument or wondering whether or not a certain thing that they're saying is a tautology, or whether or not what they're saying is valid or something, you can apply this to check to determine whether or not it's the case. Like someone asked me the other day on Google Plus whether or not a certain argument. They were asking me whether the such and such counted as a valid inference, and I wanted to be able to say, well, just write out the truth table, do a tree, just check kind of thing. But they didn't know this, so I had to just explain it like in words or something. But after you get to grips with this stuff, you won't need to ask someone who knows this stuff or whatever. You'll have a technique that actually gives you the answer in every case, assuming what you're talking about is propositional logic anyway. There's nothing that escapes these rules, so you can always check it. And I think that somehow that don't know what that says about my personality, but I find that is satisfying as well, that there's a test that has no gaps in it, and there's a black and white yes or no answer in every case, and something about that appeals to me. It's a sort of control thing, I suppose. There's no sort of uncertainty or waffle or whatever. It cuts straight through yes or no, black or white each time.
The problems then just become sorting out whether the premises are valid.
The premises are true.
True.
Don't you dare call valid. What the heck is wrong with you?
Come on, now, gee. Come
There's a
on.
skin crawling moment.
Have you
Okay,
got nothing?
let's move on.
Yeah. Okay. Good. So now we'll do an negated conditional. So all it is a one premise argument. So we've got not if P then Q, therefore not Q. So we write out the premise, not if P then Q, and then we negate the conclusion, so not Q. As I said already, always kill the double negation straight away so that you don't forget about it. So let's get rid of that. And then we unpack this molecule. So we apply our negated conditional rule. That means we write one branch underneath it with the antecedent, and then underneath it the negation of the consequent. So that's me applying that rule there. That means I've unpacked everything. Well, there's only one branch, isn't there? It's obvious. And also equally obvious that there's a Q and not Q is in there, so it's contradictions. That means that that branch is inconsistent, and we can close it. Therefore, the argument was valid. So
Yay.
if it's not the case that if P then Q, that means that not Q is the case.
Yep.
Anyway.
Yes.
So let's have some new, the last rule. So this is the biconditional rule, the double arrow. So unnegated A if and only if B. We write one branch on this side that's got not A and underneath it not B, and another branch we write both A and B underneath it. And on the other side, these two, I'm just going to talk about them both together straight away. So the negated rule has, on one hand, has one of the things with the negation of the other, and then the other branch has the opposite way round. And the reason that we do that is, if you think about it, the top row, so look at this hand side, right? The not A and not B underneath it. Well, that's one of the ways of making it true, right? This unnegated biconditional. That's true when both of its elements are false.
Yeah.
The other way of doing it is
if they're both true. Yeah.
Is if they're both true, right? Basically, biconditional just says that whatever's on each side have the same truth value as each other. It's the relation of equivalence. And equivalence just means the same value. So A if and only if B means A is equivalent to B, and that means that they have the same truth value. So it just says either they're both true or they're both false. It's not telling you which one, but it's saying that they have the same value. And obviously, if it's negated, then that means that they have different values. So either one's true and the other's false, or the other way around. So that's why we have the rules for this one. I think it's very straightforward, really, isn't it?
Yeah, that makes very, very good sense. Absolutely straightforward, for me at least.
Excellent. Okay. So let's just use these in an example. So first of all, here's our argument. It says P if and only if Q, R if and only if Q, therefore P if and only if R. So we write out the premises along with the negation of the conclusion. Let's unpack this. So first of all, we apply our unnegated biconditional rule. So we write out both of these negated on this side and both of these not negated on this side. Doesn't matter which sides you pick, as long as you make sure that you've got one branch with both of them negated and one of them where they're not negated. Do the same thing. Here's exactly the same rule, but for Q's and R's. So I'm applying it under each open branch. So I'm unpacking this molecule, but because there's two open branches, I'm going to have to write it out twice. So I'm putting it once down here and once down here. Everyone can see my cursor, right?
Yeah.
Yes.
Okay.
Yes. Okay, good. So I've now unpacked the premises, and I can already see, can I? Yes, okay, good. I can already see some contradictions present. So in this branch, I can see that it's Q and not Q. And on this branch I can see Q and not Q as well. So I can close those branches. Don't even have to unpack the conclusion. So it's like if you see on your way that there's a contradiction, you can just close these branches. If you don't notice it and you unpack all of the molecules and then check, you'll still get the same result. It just makes it easier to draw slides if you close the branches that don't need to be kept open. So anyway, okay, let's unpack the final part of it, the negated conclusion. Well, it's the negated biconditional rule. So that just means that on the left-hand side and the right-hand side, both have, one has to feature the left-hand bit negated and the right-hand bit unnegated, or the other way around. And we've got 2 open branches left, so I'm going to have to apply this rule twice underneath each open branch. So there we go. It would be like this. So basically, let's just have a look at it in more detail. So we've got a left-hand branch here that's got this guy along with the negation of this guy, and the right-hand branch has it the other way around, the negation of this guy along with the unnegated version of this guy. And it's exactly the same as what I've got on this side as well. So all very, very straightforward.
Yeah.
And we just check to see, because we've unpacked everything at this point, but this is the last thing that needed unpacking. So we know that all we need to do now is just check branches to see whether or not we've got a contradiction. Lo and behold, we do. We've got P and not P in that leftmost branch. And the next one in, we've got R and not R. I suppose let's make it slightly more interactive. Is there a contradiction on this sort of third or first remaining?
There's a P. There's a P.
Yeah, you've got a P and an R contradiction.
And you only need one, too, right?
Yeah.
So,
In fact, they both got contradictions. One, there's a P at the.
There's a
Wait,
P and a not P. P
Yeah,
at the
that
top level
P
and
with
a
the
not
P
P at
above
the
it,
bottom
yeah.
level.
So,
hold
yeah,
on,
we've
let's
got-
do the left branch first.
Yeah, so
R,
left branch first.
not R and R.
Not R and R, yeah.
Yep.
Good, good. It's all very easy, isn't it? Look, there it is.
And there's the not P and P right there. Yeah.
Not P and P. Great. It's
Don't
obvious.
be
It's really easy.
marking up your screen.
Yeah. So this is obvious and easy, isn't it? Really, what I'm doing. There's nothing complicated here. It's just learning things.
Yeah, the only thing confused me early on when you talked about these trees, couldn't see where this tree was coming from and going to. Now that and I always wanted you to put something needed unpacking as the second premise to work out where your tree was emerging from. Now you've put a biconditional, a binary thing, something needed a molecule in there. It's now made it clear where this tree's emerging from and going to.
Okay,
Yeah,
good.
when I was practicing, I had to number them, right? But if you just number them, like put a little 1 at the first one and a little matching 1, then you know it's really clear what he's doing when.
Okay, see,
Okay,
personally, I'll try and organise. I would remove the premises from this and stick them in another column well away from the tree, and then just have the tree starting off.
Oh,
yeah,
I see.
I was wondering about that. Can you do that? Because it seems to me like that would be a perfectly legit thing to do.
Yeah.
But I've never seen anybody do it.
Mhm. Well, you could do. So you just mean writing.
That's what seemed messy to me. You're messing up what your premises there with the tree you're creating. That should be a separate thing as far as I'm concerned.
You
But,
could put a line under it.
yeah,
Well,
that sort of thing. Yeah.
It seems to me that if you're going to make a tree, then it needs to have a trunk. And if I put all of these on the other side, then it would be a bush, not a tree, because it wouldn't have a trunk on it. So,
Yeah, and you should. It's also worth being mindful. As you're looking through the branches for contradictions, you're often looking for contradictions in one of the branches or twigs with something that's on the trunk. The premises are not there just hovering. The premises are part of the propositions that are being tested for contradiction. In this
Yeah, but
case,
if you do
No,
that,
they're not.
No, I agree, they're not. Because if you do that, you're going to get confused.
there's one right there.
yeah. So hog
Yeah,
ties.
but it shouldn't
Wait a minute,
that's
show
what's-
us that again.
Yeah, but it shouldn't be. Yeah, but it's only because it hasn't been unpacked. So you've got a different.
No. Look, so Hogtie's right here, because look, say the second premise, right? It is P. It already is just a single atom premise, right? And that means that when we unpack the stuff, that second premise is part of the branch that we're looking at. So if I'd written all of the argument over to one side, then the remaining parts of the tree wouldn't be enough to show me that there was a contradiction. So actually, Hogtie's right. It's not just my flippant answer.
Okay, all right, but
it's actually
I suppose-
it's necessary in order for you to be able to see easily that there's a contradiction. You have
Okay,
to
what I
conceive
would have
about
done is I would have
the tree.
I'd effectively unpacked my little list and then put that into go through the list and then put those into the trunk, which would obviously start off with the premises, I suppose, is what I'm saying. But yeah.
Yeah, so just do it the way I've said. You'll be fine.
Yeah, I certainly don't
If you
object to
just
the.
drew a line underneath the trunk, that would solve the issue that's bugging you, and it would also keep the premises where they need to be as a trunk like that. Would that be something that would work? Just draw a line?
If you want to draw a line, as long as it doesn't confuse you, yeah, then fine, absolutely. You wouldn't lose marks for drawing a line, say in an exam or something. But the point is, it doesn't matter what you draw on a piece of paper, right? As long as you get to all of this, it doesn't matter. If you do it in your head, then great. You don't have to write anything down. The thing is, if your test reliably gives you the right answer, great. If you want to draw an extra couple of lines, smiley face, whatever, I don't mind. But as long as you're doing enough to get you the right answer, and you understand from what I'm showing you how that you're guaranteed to always check for invalidity, then that's fine.
Well, Holtei's point about the premise only exists if it's the atomic thing, if it's a molecule like that, you see, it's not participating. For instance,
that's true.
Yeah,
but
so that's why I felt it was invalid to say that.
Okay.
Well, I do applaud the effort to a little bit of extra note taking too, especially when you're learning it and you're practicing and you're worried about this thing about missing a step. I do like when you have a molecule to put a tiny little number in a circle off to one side.
No, you have to use a smiley face, obviously.
Smiley face, whatever works. Yeah, and then when you have when you accommodate that branch, or that molecule by decomposing it somewhere else on the thing, to then at the little junction. Then put that little number in a circle again, and then I'll even put like a thin line through the molecule above, just so I remember, okay, yeah, at number 3 I've dealt with.
Yeah.
Well, but isn't that redundant?
Well, I'm mindful of, the things, we're not necessarily in a race when we do these things, but I'm mindful of there is a danger of if you miss one of the decompositions, if you've got the decompositions, if you miss one, you're taking your molecule, if you leave one and I forget it. There's a concern
I know what you're saying. I was
one.
just playing around.
Okay. There's a concern if you miss one that you might miss a potential contradiction.
Mm-hmm.
Why would that not work in your favor? Go ahead.
No, it absolutely works in your favor. You could number them and smiley face them, and cross them off. Then you'd really be sure.
So, like I was doing, sort of implicitly, like although I didn't do it with this one, but up till now, I'd been greying them out when I'd unpacked them. And, right, so here, I've unpacked everything that needs to be unpacked, and all that's left is the branch to check. And by greying out is my way of telling myself that I've finished unpacking everything. So
just imagine there was a second premise between those two molecules. There was another one that you didn't unpack. Say there was one between the P and the Q. You would have to leave that there. So you'd have a limit. You have grey ones interleaved with non-grey ones, and it just looks horrible.
Sure.
Oh, I've got a solution for that. Put all the ones that don't branch. Do those guys first, and then do the branching ones. There's like a sort of an art to this, which is so we're talking now about the aesthetics of trees rather than the actual.
Well, this is what annoyed me at the start. Yeah.
But what you're worried about is not something that would actually make a difference to whether you got the right answer or not. What Hogtie was talking about a moment ago was a pragmatic thing that you need to do in order to make sure that you get the right answer. It's part of the method being a proper method that we can use. Well, yes, there is, as far as the aesthetics go, there is a school of thought which says that you should always do the non-branching.
Exactly.
Non-branching rules first, and then do branching rules afterwards, so as to minimise the amount of duplication that you have to write.
Exactly. That's the sort of thing I'm thinking of when I didn't like the way it was ordered. But anyway, I think we all agree with you're going to the right thing, so we could probably move on, I suspect.
Yeah.
I agree. Let's move on.
Okay, great. So that's pretty much the end of this. That is, in fact, the end of this set of slides. So I'll move on to the second set. Just give me 1 second. Oh, Christ, what do I do? Oh, Jesus Christ. I've completely forgotten how I screen share this.
So screen share is the second little button there on your left. And then I'll go ahead and broadcast you. So just screen share the one you want, and then I'll just make sure that it's always the thing that's up.
Let me just get, so we're on 8 now, aren't we? Yeah, okay, good. So this is the last bit of tree proofs for propositional logic. So can everyone see that new slide?
Yep.
Yeah. Okay, good. That's no longer my email address either, so don't email me at that address. All right, cool. So before we plow into this, I'm going to give you a few more examples. Then I'm going to show you what happens if a tree doesn't close. And then I'm going to talk about soundness and completeness. We've got an hour, so hopefully I'll try and get through this within the first half an hour, and then we can talk a little bit about material implication in the last bit. Because that'll be a bit less just do a load of rules and here's a load of things, and will be a bit more philosophical. So, all right, good. This would be like the break in between the half of the course that's on propositional logic and the second half, which is on first order logic. So this is the last bit of propositional logic we're going to do. So yeah, I don't know. Anyway, let's just recap what we just did before. So here's our argument here. It says P or Q, if Q then R, not R, therefore P. So we write out all the premises and along with the negation of the conclusion. Let's start unpacking the premises. So we apply the unnegated disjunction rule first. We can already see a contradiction, so we can close that branch, which is nice. Let's apply the unnegated conditional rule. So that means writing not the antecedent on the first branch and then a right-hand branch of whatever the consequent is. Now we can see already that there's a contradiction there, so we can close that branch. And then on this other branch, obviously R and not R, there's a contradiction there too. So as all of the examples we've had so far, the tree closes, each branch of the tree closes, and that means that there's no consistent way of making the premises true along with the negation of the conclusion. And that means that if the premises are true, the conclusion has to be false, and that means that the argument is valid. Okay.
Good. Good.
Okay, good. So let's look at trees that don't close. We'll look a bit more at comparing trees to truth tables, and then we'll look at soundness and completeness. Right, so as I said, we've seen lots of trees that close. All we've done so far is seen trees that close. And when they do, then we conclude that the argument is valid. But what about when it doesn't close? Well, I've already talked about this, so we know what it means. So if we've exhausted all the rules that might be applied to a tree, that means unpacked all the molecules and killed off all the double negations, and there's still an open branch, then all of the formula in that branch might be true together. And that means, as we'll see in a moment, that there's a truth assignment on which all the premises are true and the negation of the conclusion is true, which means that the premises are true and the conclusion is false. And that means that the argument is invalid. So if there's an open branch, then after all of the rules have been applied and there's nothing else you can do, if there's an open branch, then the argument is invalid. So open branch means invalid. So if the thing finds what it's looking for, which is an open branch, then it's found a truth assignment on the truth table where the premise is true and the conclusion is false. So that's what I said before. It's like a sniffer dog that's trying to find that. And
yes, that makes perfect sense.
So that's the test that we're applying. And so far, every time we've applied the test, it's failed. And that means that we've shown that the argument is valid. It's a bit counterintuitive because most of the time the kind of positive property that we're looking for with arguments is whether they're valid or not. And it's a bit weird to have a test where it's looking for invalidity. Nonetheless, that is what we're doing here. Okay, good. So, and then I'll show you that from the open branch we can read off what the truth assignment is. And we say it's a truth assignment that witnesses this. It's the way that the world could be if the premises were true and the conclusion was false. Right, let's see how then. So here's an argument. If P, then Q, Q, therefore P. Anyone know what the name of that fallacy is if you try and say this as an argument?
It's called the modus ponens or modus ponens fallacy.
It's
That's what I've always called it. I've always called it that by that one long name because I can never remember.
It's affirming the wrong thing. It's affirming the consequence.
Yes. There you go.
Yeah.
I'll just use that.
I got in there before Rumpus.
Damn.
I'll just start calling it that now instead of trying to remember the long name.
Yeah, or you could randomly use your own word, like asserting the consequent.
Oh, good. That's a good reference. I like that.
Yeah.
I gotta go.
Wrong, so.
Yeah, I'll watch this later. I'll see you guys later.
All right, take it easy. Okay, good. So here's our. I've just done it all in one step, basically. There was only one thing to unpack, and I've unpacked it. So that branch doesn't have a contradiction on it. It's just got a Q and then 2 instances of not P. There's nothing else to unpack. So I can't apply any more rules to try and find a contradiction. There's nothing else to do to this branch. And that branch doesn't close. So we don't even need to worry about the rest of the tree. We can forget about it. As long as you find an open branch and there's definitely, you've ticked them off or you've numbered them or whatever, and you know there's nothing else to do. If you find one branch that doesn't close, you're done. Game over, because that's the test that you're trying to find. So, you might luck out one day with a really, really big tree. The first one you test doesn't close. You can stop doing the rest of it. You don't even need to worry. So
we don't even need to know that the other side doesn't even work. If we get one, we're done.
That's
right?
it, yeah. Because all it's saying is that there is a way that the premises can be true and the negation of the conclusion. Yeah, what we're saying is that the premises and the negation of the conclusion can be true together.
Right, and that's a crazy world.
Yeah, but that means that. Wait, I'm confusing myself.
Yeah, that's okay. I think I got you. So just keep going.
Yeah. So if there is no inconsistency or if there is no contradiction in your tree, you know it's an invalid argument. Correct?
Right, because if the premises are true and the negation of the conclusion is true, that means that the premises are true and the conclusion is false.
Right, and that's just
That's
crazy.
an invalid argument. Well, that's the definition of an invalid argument. The definition of validity that we started with was saying if the premises are true, then the conclusion is true. So if there's any way, even just one way, of making the premises true and the conclusion false, even if it's just one way of doing it, that just means that the truth of the premises doesn't guarantee the truth of the conclusion. Right? So even if, like, I don't know, most of the time the premises being true comes along with the conclusion being true, if there's even one where it doesn't, that means that it's not valid, deductively valid anyway. This is what deductive validity means. So that's why, in this case, you only need to find one branch that stays open for you to know that you've done your test and you found that the argument is invalid. Invalid doesn't mean if the premises are true, then the conclusion is false. It just means that there's a way where the premises are true and the conclusion is false, i.e. it's not the case that if the premises are true, then the conclusion is true. Right? So I can remember talking to someone before, relatively senior in philosophy, although admittedly not in logic, who had an argument or a debate with a student in class where they were saying, the teacher was saying, a valid argument is when if the premises are true, then the conclusion is true, and an invalid argument is when if the premises are true, then the conclusion is false. And the student was saying, no, that's not it, that's not right. And I can remember settling it and saying, sorry, in private with this person afterwards, I'm sorry, but on this occasion the student was right and you were wrong, and they had to go back and sort of publicly say, yeah, actually that's true. I'd misunderstood. So validity is, I'm going to say it one more time, if the premises are true, then the conclusion is true. Invalidity just means that's not always the case. There's at least one way where if the premises are true, the conclusion is false, and that's it. Okay, so validity is a strong property. Invalidity is, in a sense, a weak property. That only one instance of it needs to be the case, of true premises and false conclusion, for it to be invalid. That's it. Only one thing needs to come along. It's like if it's impure in any sense, then it's not valid.
Yeah.
Okay, cool. So, right, from each open branch, technically we have got 2 open branches here, but whatever. From each open branch, read off the truth assignment that makes all the formula true on the top of the tree. So we look to the propositional letters and their negations, i.e. the bits of the branch. If a propositional letter appears unnegated in the open branch, the truth assignment makes that letter true. So in this case, P, well, that appears unnegated in the branch. So we would think the truth assignment is that, sorry, what am I talking about? Q here, this is a Q, right? It appears unnegated in the branch. So the truth assignment for Q is true, right? And then if the propositional letter appears negated, like P does, then the truth assignment for P is false, right?
Yes,
So
you're relating it to a truth table, and in my mind, that's what you're doing right now.
Yeah, that's it. That is exactly what we're going to do. And obviously, because it can't be the case that both occur, because if they did, we're not going to get true and false, because the rules are if it's unnegated, then it's true. If it's negated, then it's false. You're never going to get through it with both negated and unnegated, because otherwise we would have closed the branch. And by definition, that would have been a closed branch. If it's an open branch, we know by definition that we're going to be able to not get inconsistent truth assignments.
Right.
We're not going to get both true and false.
Right. Okay. Yes.
What we'll see later is that it doesn't guarantee that it's a maximal truth assignment, and that means that we're not going to necessarily have each propositional letter appearing that features in the argument. But that doesn't matter, because always I'm confusing things a little bit, but sometimes you don't need to specify the truth value of a particular atomic proposition, because you'll find that there's more than one row of the truth table where the argument has true premises and a false conclusion. And say if there's two rows, it might be that on one of those rows R is true and on the other one R is false. So you don't actually need to specify R. But the tree method guarantees that it will give you a truth value, a consistent truth value for each of the propositional letters that you need in order to find at least one row of the truth table where the premises are true and the conclusion is false. So it gives you enough, and it guarantees that it never gives you both true and false. Never
so it gives you a minimal idea of what would make it whatever you said, maximally true or something, or
yeah. So by saying so if it was maximal and consistent, that would mean it would give you every single row of the truth table where the premises were true and the conclusion was false, and it would never give you one. It would never assign both truth and falsity. So it would give you
minimal. So that's the minimal one, right?
Yeah, it's actually somewhere in between minimal and maximal. It's sort of sufficient. It always guarantees to get you enough. It doesn't guarantee that it'll give you. Sometimes you'll get a redundant letter in there.
Right.
Sometimes, but you'll always get the necessary letters in there.
Right.
Anyway, this will make more sense later on. So here is the argument. So I'm just moving this to the middle of the screen. It's not a new argument. And we've got our open branch. And now what I'm doing is I'm applying what we just learned on this screen about getting the truth assignments for reading a truth assignment off an open branch. And then I'm going to do that, plug it into, this is like a single row of a truth table. The truth table in this case would have 4 rows, but we just need to think about this one row in particular that we get from this branch. Now,
yeah, so it picks out the row where you've got the problem.
Yes, that's right. So because P appears negated in the branch, then underneath P, we're going to write F, right? Because if not P is true, then P is false. And then because Q appears unnegated, then underneath Q in the truth assignment we write true. So now we've got a value underneath the atomic letters in our truth assignment part of the truth table. That means that we could fill out the rest of the truth table. So first thing we do is we just put underneath P's in the rest of the truth table, we write whatever it says underneath P in the truth assignment, and then the same for underneath Q, we write whatever it says underneath Q in the truth assignment. And then we know how to fill in. We need something underneath this conditional sign. Well, we know how to fill that in because we know what our truth table is for conditionals. So does anyone tell me what we're going to put under here? What's the truth value of a conditional if the antecedent is false and the consequent is true?
True.
Yeah.
It's true, yeah, great, because there's only one way that a conditional is false, right? And that's if the antecedent is true and the consequent is false. Any other way, it's true. In this case, that's true as well. So what we've got now is premise true, conclusion false. And so that's an example of how this argument isn't valid, because it's not the case that if the premises are true, the conclusion is true. Here's a counterexample, right? The premises are true and the conclusion is false. So this is why affirming the consequent is a fallacy, because it doesn't guarantee you that the conclusion is true. Sometimes affirming the consequent means that you get a false conclusion. So you can't guarantee if you say, look, if P then Q, Q therefore P, that doesn't mean that P has been established. P could still be false.
Yes, P could still be false. That's exactly what it is.
Right, good. So you don't need to worry about, is that right, is it not? You could do a test and get the answer. This is the test to get the answer. Okay, good. So we know that that argument is invalid because of what we've just done there. Let's do another one. Slightly more complicated argument. If P then Q and R and S second premise, R or P, conclusion, Q if and only if R.
Wow, I can't think of a language example.
No, don't try and think of a language example.
Okay, okay.
So, yeah, that's right. Just apply the rules without thinking about it in terms of, Johnny went to the store and Bob went to the store. So it doesn't matter. These are just like algebraic rules that we're learning and applying. Anyway, so we write out the premises along with the negation of the conclusion. Same thing every time. Doesn't matter how complicated the argument is. You're doing the same thing every single time. And then all you need to do is unpack those. I've just done it for us, right? Because it would have taken a few moments, but really nothing complicated. It looks quite complicated, but really it's not. All of it closes except for this one branch here, the second branch. It's got this branch, right?
Yeah.
It's consistent, which is nice. There's no formula appears along with its negation. That's why we haven't closed it. That means that we can read off a truth assignment for it. So let's have a look. P appears negated, so underneath P we would write an F. And all I've done with the rest of this is I'm just putting the premises along with the conclusion in the truth table, right? I'm not now putting the negation of the conclusion, I'm just putting the conclusion.
Yeah.
Because I just want to show you the premises being true and conclusion being false. So it's,
yeah, because the whole point of just negating the conclusion was to find this tree.
Yes,
exactly.
Yeah,
yes, and now we're picking out the row that shows what the tree is showing.
Yeah, exactly. So P appears negated, so we put an F underneath it. Q appears negated, so we put an F underneath it. R appears 3 times without a negation, so we put a T underneath it. And S also appears on its own, so we can put a T underneath it. So now we've got our truth assignment. We can pop in all of the things underneath it. No surprise how it works. It's just a mechanical application of the rules again. And we find that the main connective of the first premise is true, the only connective, but the second premise is true, and the main connective, only connective on the conclusion is false. So again, it's an instance of a truth assignment, a way that the world could be, if you like, where the premises are true, but the conclusion is false. So obviously it's not the case that if the premises are true, then the conclusion is true. It's a counterexample. So it's showing you the argument is not valid.
I get that. I get it.
Great. So what this shows, I think, is that like most of the ways, because most of these branches close, most of the ways that the premises are true, it doesn't rule out the conclusion, or most of the ways that you can assign truth to the bits of the formula. Let's be clear about it. Most of the ways you can assign truth to the P's, Q's, R's, and S's doesn't mean that the premises are true and the conclusion is false. It might make the conclusion, it might make the premises true, it might make one of the premises true and the other one false, or something like that. Any other pattern of T's and F's, right? Most of them don't tell you whether or not it's invalid, right? But you only need one. You only need one to tell you that. So this might be the only row of the truth table that shows you this, but that's all you need.
Yeah.
Anyway, okay, good. Right, let's talk about soundness and completeness. Okay, so we've got our 2 tests. And what we want to do is, so we've got our notion of validity, which just means that an argument is valid when, if the premises are true, the conclusion is true. That's just what it means. And we've got our 2 tests. We want to make sure that those tests are adequate to checking for validity. And there's 2 ways that each test could fail. So I'm ad-libbing, but let me make sure I stick to the script, I suppose. But so, yes, we've got our 2 tests. They're just rules, they're just mechanical procedures, and we can just apply them, mindless application of rules, and they always give us a verdict, which is cool. So there's 2 properties that these types of tests can have. The first one is called soundness. And don't get confused between sound. A sound argument just means it has true premises. And what we're talking about now with soundness is it's related, but it's a property of the proof theory, i.e. it's a property of truth table method, or a property of the tree proof method. And we're talking about if that method is sound, it means that whenever it gives a positive answer, then the argument form is valid. Actually, that's wrong. Well, it depends how you gloss that. I've been talking about positive answer in the tree proof method being showing that the argument is invalid. but either way around, doesn't really matter. If the test passes, however you want to think about that, then it shows that the argument is valid. Whenever the test fails, it shows that the argument form is invalid. So there's two ways in which the proof theory might fail to correspond to the notion of validity. It might tell you that something's valid when it isn't, or it might not tell you something's valid when it is, right? So that if both of these properties are made, if we can show that it's both sound and complete, right, that means that the proof method sort of maps perfectly onto validity. It means we're never going to go wrong with it. So as a test for determining whether an argument's valid or not, it's always going to give us the right answer. Does that make sense?
This definition of sound, is that the same one as saying that if your premises are true, your premises have to be true? Sorry, I lost with this. Is this the use of the word sound was used to describe a valid argument that has valid true premises?
No, I think it's different.
Okay, not the same.
Okay, right.
We're talking about testing the theories of these two methods.
Yeah, that's right. So what we're talking about is, so we've got a split between logic, which is like our formulas, the way that we can put those formulas together to make a well-formed formula, the way that we can arrange them as premises and conclusion form in an argument, and along with the notion of validity, which means, as we said, a valid argument means that if the premises are true, the conclusion is true. We can sort of think about all of that on the one hand as being logic, right? It's just premises, it's well-formed formulas, and it's arranging them in such a way that they make arguments. It's where an argument is valid if it has that property of preserving truth from premise to conclusion. Now, that's logic. Now, on the other hand, we've got proof theory, which is actually doing some mechanical tests on the logic to see whether or not it's got a property of validity, or if it's an argument, or if we're looking at a formula on its own, we're testing to see whether or not it's got a property of being a tautology or whatever, right? So we've got a proof theory, which is a way of interrogating the logic and testing it to see what properties it's got. Yeah. And what we're saying now with soundness and completeness are properties of the proof theory. So they're not properties of arguments, because that's over in the logic. This is properties of the proof theory. Does it work? Does it interact with logic properly or not? And fortunately for us here, obviously I wouldn't be using it if it didn't, but both of the methods that we've got are going to pass both of these tests. So that means it's going to capture our notion of logical validity in such a way that whenever the test says something's valid, it is valid. And whenever the test says that it's not valid, it isn't valid.
Right.
Right. So, like I said, you don't want the test to tell you that an argument is valid when it isn't. Otherwise, it's not a good test. You don't want the test to tell you that something isn't valid when it is. Otherwise, that's not a good test either.
Yeah.
Yeah, that makes sense. What I'm not quite sure about what completeness is about.
Oh, completeness is just this bottom bit here. So the test is complete whenever it gives a negative answer, the argument's invalid. So whenever if our tree method, say, told us that a particular argument was invalid, but actually it wasn't invalid, it was valid, then the tree method would be incomplete.
Yeah, it was the second explanation he gave a moment ago before.
Yeah. So it would be it not telling you that an argument was invalid when it was.
Yes. So that's the expression he used. Yeah. It wouldn't. Yes, it's not telling you that an argument is invalid when in fact it is.
Yes. Exactly.
So
when you're doing this soundness and completeness sort of proof thing, you kind of want to redo your thinking on the trees, because even though the mechanics of the trees make what's invalid stick out, in order to follow this test, I hope I'm thinking about this correctly, you need to kind of reverse everything so that you can really see that it's actually about validity.
Well,
no,
I think all that I've been doing that was, I suppose, somewhat misleading is I've been saying that you consider it as a test to find invalidity, and it passes if it finds that invalidity. All you need to do is switch to it.
Yeah, switch those around.
All you need to do is switch around pass and fail.
Right.
It's still the same test. It's just whether or not it passes or fails is the other way around.
Okay.
So because it's been a few years since I even looked at these slides, and I hadn't had a chance to think about it before I started talking today. So
no, you're doing very well, Alex. I think to remember, to swing it just from the standing start. I think you.
Okay, good. So
okay, so it's sound when it gives a good answer. Hold on.
Let me try this. If what I'm hearing is the test is complete, meaning that you can't go further with it. It stops right there because there's nothing you can do with it because it's invalid. Does that make sense?
No,
I can see where you're going with that, but that's not. I mean, in a sense, the test does have the property that you're saying. Once you found that the argument's invalid, you don't need to go any further. That's true. But that's not what this means by complete. I suppose what it means by complete is there isn't an outstanding. If it says that the argument is invalid. No, okay. So if it says that the argument's not invalid, there isn't an outstanding case that you haven't covered yet that shows that it is actually valid.
Yeah. Okay. I
so
see
there
that with the
isn't
tables.
anything that you haven't covered.
Mm-hmm.
Regardless, I think we could just call this the test is positive, or at least the proof theory is adequate if there were, and there's two aspects to it. And we could call it schmerb and blurb. Right? It doesn't really matter what these words are. Right? The test is schmerb if whenever it gives a positive answer, the argument form is valid, and it's blurb if whenever it gives a negative answer, the argument form is invalid. Let's spell this out in a bit more with some examples so you can hopefully see what I mean. Okay. So let's look for soundness first. So suppose that an argument passes the truth table test. Right? So here's an argument where the premises are if P then not Q, P therefore Q therefore not P. So no, if it passes the test, then no row of the truth table makes the premises true and the conclusion false. Now I've highlighted this row because, well, it's the only one that had both of the premises being true. And in that row, because right, so first row, that premise is false, so we don't need to worry about it. In the second row, this premise is true, but this premise is false. So these aren't going to be instances where the premises are true and the conclusion is false. And same with the bottom row, the first premise is true, but the second premise is false. So that's not going to be one either. At least with this one, you're kind of almost there, because at least the premises are true. But in that case, the conclusion is true as well. Right? So there's no row where the premises are true and the conclusion is false.
I get that.
Right, so what we're saying is that the truth table method is telling us that the argument is valid because there's no way that the premises are true and the conclusion is false. Right, so the truth table method is giving us a positive answer. It's saying that this argument form is valid.
Yes.
And then, but now we're wondering, well, is it though? Is it actually valid? Can we trust this answer, or is it giving us a wrong answer or not? But we can, because in a sense, we can test this by running through all of the possible ways that the premises could be true or the conclusion false. Right? There really isn't another way. Right? What other way could there be that makes these premises true and the conclusion false? Right? How could we? Couldn't be a fifth row.
Right.
But because we've exhaustively run through all of the different combinations of true and false, and that's all that there is to it. So we know for sure that definitely, provided you filled in your truth table correctly and you've got the right number of rows on it, I guess. But as long as you've done that, you know that you can trust the answer that it gives you in this case. Right? If there's no row there,
this method.
Yeah, that's what you can trust at least the positive result that it's giving. It's telling you, look, the argument is valid. And you know that you can trust it because you know that there aren't any other cases that you haven't thought about. It's got them all here. Right?
Mm-hmm. Yes, yes.
So there is no possible truth assignment that makes the premises true and the conclusion false. So we know that when it says it's valid, it is actually valid. So that means that we can trust the positive results that it gives us, so that it's sound.
Okay.
Completeness is kind of the other way around. Suppose the argument fails the truth table test, right? So here's kind of very, very similar argument, but just slightly the other way around. If P then Q, Q, therefore P. This is what we just saw a moment ago, asserting or affirming the consequent. Now we do have a row of the truth table where the premises are true and the conclusion is false, right? Everyone can see that that is an instance where the premises are true and the conclusion is false. So obviously it's not the case that if the premises are true of this argument, then the conclusion is true. Right.
Yeah. Yep.
But obviously it corresponds again that if that's the case, since each row is a possible truth assignment, and there is a row where the premises are true and the conclusion is false, then there is a truth assignment. There is a way in which the premises can be true and the conclusion false. Yep. So that means that if we try and test this argument to see whether or not it's valid and it fails the test, or if we run it through the other way around and say we're testing the argument to see if it's invalid and it fails the test, that's the locution I've been using so far, but whatever, it doesn't really make any difference. The point is, if we're applying the test to see whether or not it's valid and it tells us that it's not valid, then we know that it is in fact not a valid argument. So the truth table method gave us a result, and we know that there is a way of making it such that, it's not like this row just I plucked it from my rear end without any justification for it. There's a truth assignment that goes along with it. That's why, that's what this row is. So there is a way. So what we're saying is there is a way of making the premises true and the conclusion false. This is the way.
Why was there any doubt about this? I'm a bit confused as to why there's any doubt about this, given that the soundness one.
The soundness one, or the completeness one.
Yeah, no. Why is there a dispute, a possible dispute about the? Why is there a potential dispute? Why are you having to go through this again when you've already shown that the argument is invalid?
Well, what I've done is I've shown. So the truth table method is basically I can't highlight the right rows, but it's everything apart from this truth assignment bit. Right. What we're doing when we're making the truth tables is building a kind of machine into which you can put the basic true or false of each of the propositions, and it'll give you a result back for whatever argument you want. And now that isn't logic, that's the proof method. And the question is, we've got logic, as I said before, logic on the one hand, which is just these formulas, the fact that some of them are true, some of them are false, and the notion of an argument being valid if it preserves truth from premises to false, from premises to conclusion. And then what we do is we say, okay, well, I want to sort of model that to see, to check when someone's using an argument. What do I need to do to make that test? And one answer to that is you say, okay, here's this truth table method. Now, does the truth table method actually give me the right answer each time? And I know it's pretty obvious because, in a sense, of course it does, right? Of course it does. How could it go wrong? Yeah, you're right. It can't go wrong. Well, our point is it can't go wrong, right? That it's both sound and complete. So showing you that it doesn't go wrong is just showing you an instance where it works properly, and it always works properly. So, I mean, in a sense, it's very, very difficult to. What would make this easier to understand, I guess, would be if I had an alternative proof method that failed.
Yes.
And the thing is, it would be very contrived to come up with a proof method that failed for propositional logic, and it would seem really, really stupid if I started saying, here's a method and it tells you the arguments are true, but it doesn't. You don't have to check whether the premises are true and the conclusion is false. It just tells you it. Like I roll a dice, and if it comes up 6, then the argument is true or something. Right? That would be a method that's neither sound nor complete, because sometimes it tells you that an argument is valid even when it isn't, because rolling a dice hasn't got anything to do with the properties of this argument. I suppose that's quite a good example, actually. So yeah,
this makes sense. I like this.
Now the thing is, when you go into higher order logics, it starts to become these properties fail, and I'm not going to, because I haven't thought about this at all for ages. But everybody knows that, well, not everybody, but often you hear this chucked around on the internet by people that this logician Kurt Gödel in the 30s proved that arithmetic was incomplete. He has its famous incompleteness theorem.
Yeah.
Now, it's completeness in this sense. It's just showing you that that there are formulas which are valid, but which you can't prove that they are.
Yes.
You should be able to prove that they are, but you can't. Right? That's what Gödel showed with his incompleteness theorem. Is that in a very sort of profound sense, mathematics can't be modeled in such a way that you could prove every formula in it. And the formula that he's got is quite an artificial one. It just says something like arithmetic is consistent, and you can't prove that formula is true. So it's not like a number theorem like 2 + 2 = 4 or something. You can prove, I think, I might be overstepping this somewhat, but I'm pretty sure no mathematician's actually given an example of a piece of arithmetic that you can't prove. It's just that there's more to mathematical logic than that. And there is, in a certain sense, arithmetical sentences that you won't be able to prove. So it's defined by this type of logic called the piano arithmetic, where I'm getting massively off track here.
Yeah, perhaps. Yeah.
The point is, though, that all I want to say about it is that part of the reason it's nice to show that this works here is because it does work. And it's like a very useful property that these very basic logics have, which is that you can prove everything that's true in them, and everything that's true in them you can prove. And the fact that it goes both ways, or every argument that's valid, you can show that it's valid. And if you can show that it's valid, then it is. Right? Those are very, very useful for doing logic, obviously. Once those stop working in one direction or the other, you begin to lose the ability to do traditional logic the way that you'd want to be able to do it. So it's like we're in the paddling pool and you've got armbands on, but then sooner or later, as you wade off into the deeper waters of logic, one of the armbands falls off, and you have to try and negotiate swimming without it helping you out. So whilst we've got them, it's nice to at least show that we've got them. That's why I'm going through this.
Okay.
All right. So let's just show the same thing, but for the tree proof method. So I think hopefully I've shown you that with the truth tables, there's no way that we could have got a positive result when we shouldn't have done, and there's no way that we should have had a positive result when we didn't.
Yeah, and I understood it intuitively with the tables. So
yeah, okay,
I'm
good.
Waiting with bated breath for these trees here.
Okay, good. So let's suppose that we've got this argument and it passes a test. So by passing the test, I mean we've shown that it's valid. So the tree proof method comes out with the answer. Tree proof method said, so we've got this argument, and then we say, hey, tree proof method, what do you think about this argument? And tree proof method answers us and says, oh, I think it's valid. Now, is the tree proof method telling us the right thing when he says that to us? Well, let's suppose that he says that it's valid. Well, that means that every branch of the tree, branches being the atomic parts or their negations, if it says that it's valid, that means that every branch is closed.
Yeah.
That means that if there's a truth assignment that makes all the formula in the trunk true together, then there's at least one branch of the tree for which there's a truth assignment that makes all of its formulae true together. Let me just think about what I'm saying. Right. So if there was, yes, okay. So if there was, let's see. I think what I'm saying is that each, yes, okay, good. That's right. So basically, if this was open, then there would be a truth assignment that went along with it. But there is no truth assignment that matches this branch, because the truth assignments just have true and false and never overlap with one another.
Aha, I see it.
With each other.
Yeah, it just clicked.
Because this has got P and not P, there's not going to be a truth assignment that has both T and F under P. Right? So since each branch closes, there is no truth assignment that kind of corresponds with it. Therefore, the argument's valid. So if it passes the test, or sorry, fails the test, depending on what I said, then the argument's valid. So if the tree method says, hey, this argument is valid, then it's saying, he's saying, well, what I mean by that is if the premises are true, if we suppose that the premises are true and the negation of the conclusion is true, then
false. Sorry, I'll take it back.
No,
Yeah,
true.
yeah.
True. Yeah.
Yeah, sorry, I said that. I was wrong. Yeah.
So basically, I said, hey, I've got this argument, and then I said to tree-proof method, what do you think about this argument? And tree-proof method says, well, I think that it's valid. And then he goes, well, but let me explain what I mean. What I mean is, I'm saying about that argument, if all the premises are true and the negation of the conclusion is true, then I'm going to get some kind of inconsistency, which is going to mean that I'll close all my branches off. Right? That's what I'm saying to you. I'm saying it's invalid because I'm saying that if the premises are true and the negation of the conclusion is true, then something goes wrong. Right? And that just means that there's no way of making the premises true and the negation of the conclusion true. By no way of making, I mean there's no truth assignment that makes it so. Right?
Yep.
Any way you try and get a truth assignment that corresponds to this, the argument with the true premises and negation of the conclusion, you just can't find a way of doing that. So if it tells me there's no way of doing it, I know that there is no way of doing it, no truth assignment that corresponds to it. So I can see that the method that it's giving me is right.
Okay.
Okay. And then the other way around, let's suppose that after all the rules have been applied, there's an open branch. Okay, good. So that means that there is a way that corresponds to it, right? That I can make the premises true along with the negation of the conclusion. I could make the premises true along with the conclusion false.
Yep.
Right, and there is a way, and we know that there is a way because we can read off the truth assignment from the open branch, which is what we did earlier. You just have to say, if P appears with negation, you put false underneath it, and if it appears without negation, you put a T underneath it, and then just roll out the truth table row that you would do for that, and you'll find guaranteed every time that it'll be the premises are true and the conclusion is false. It'll be the premises are true and the negation of the conclusion is true. Same thing. Right? You're guaranteed that this will map onto this. Yeah?
Yep.
Okay, good. In a sense, you don't really need to know this. Like, you could pass the exam, not that we're sitting an exam at the end of this, but I wouldn't ask students to explain soundness and completeness on an exam for this. Like I said, it's more like something which is nice to show because we can still show it. Plus, if you feel like reading more in, I don't know, if we keep doing this forever, I would eventually get onto types of logic where these properties fail. And it would be interesting at least to know what we mean when we say, well, now at this stage we're doing a second order logic and we don't have completeness for it. And you'd say, well, what the hell is that? What do you mean? It's just nice to show that we've got it when we do, basically. And I suppose just as a sort of irrelevant side note, but Gödel proved the incompleteness of arithmetic. And I think a few years before that, so that's his incompleteness theorem. He has a completeness theorem, which comes before that, which applies to first order logic, which is what we'll go on to look at next. We're not going to look at his proof, obviously, but we're going to look at first order logic. So at least Gödel showed us that for first order logic, everything we want to be able to prove we can, and anything we can prove is something that we want to be able to prove. So that's nice as well. So we're not wandering off into too much difficulties there. Okay, so at the moment that is propositional logic. Okay, good. Yeah, so that's just the last things. It's not like we're never going to see propositional logic again anymore, because propositional logic is part of first order logic. We're still going to have P's and Q's and if and only ifs and stuff like that. They're all going to still be part of the language that we're using. It's just that we're going to add to it. So in addition to those pieces of vocabulary, we're going to introduce some new ones. And what this is going to do is it's going to allow us to be able to say all the same things as we've already been able to say, but some additional things as well. I'll go into it in more detail next time. I'm not going to start first order logic now, but we can talk more about material implication if you want now. Do you want to do that, or do you feel like there's enough material in this? I don't mind.
If you've got the extra time, I would love to hear about that.
Okay.
I'm going to make these review videos, so hopefully I get them right. And I'll go into a little bit more detail about what you're talking about, what you've just talked about. But I would love to go into the. I would love to do this extra piece if you've got the time, and especially since Rumpy's here.
Okay, good. So let's see if I can figure out how to do that then. Oh, bloody hell. Every time I try and do this, I don't know what the hell I'm doing. Is it this one?
Bloody computers.
Yeah. All right, good. Here it is. So go back here. Okay. All right, this I haven't. Can you all see that now?
No.
In lecture 9.
Oh, it's now, yeah.
Yeah,
Yep,
I just heard.
It's there.
It's there, is it? Okay, good. Is it my internet that's going really slowly, or is it everyone else's?
I don't know.
All right, whatever. So this, I really haven't looked at this at all. I mean, I wrote this lecture, so it should be all right. But let's just go into it. Yeah, that's right. All right, good. So we all didn't like this when we first looked at it. In a sense, it's got a bit of a weird truth table to it, right? Okay.
I don't know whether you. I mean, I'm intending to do a video on this because I think you're missing. It seems to me this is a very poor way of presenting it, because what it's trying to do is it's trying to relate to you the real world idea of something implying something else. So, for instance, if we go with the classic, if it's raining, then you end up the road is wet, and therefore, and then similarly, if then the position number 2, you can't have if it's true, and the B is the road has to be wet. It can't be false. So B, so that second row you've got of true false is false. Whereas and the reason the other ones are true, because in real life there is usually more than one thing that can cause something. And so I believe there should be another column there. Sorry, we're saying that what we're trying to do is represent real life. So we're saying that A, which is it's raining, and B, the road is wet. We could have another column, C, something else that can cause the road to be wet. And then we need to consider all those possibilities, and then this A implies B is then sensible, because the only thing that makes sense, because we have to allow for something else potentially making the road wet, the only possible conclusion that because the road becomes wet means that something else did it. So the only thing we know about this potential idea that we've got that making the road wet, the only logical conclusion we can draw is if it's raining and it's not wet, then there's a problem. But other than that, we then have to assume that this is an or statement. The rain could be the cause of the wet road, or something else. And this is sort of missing or that I believe that's a missing column.
I think that what you're talking about with that missing column, that makes sense the way you've described it for this third row here.
Thank you.
But explain it for the fourth row.
So I'm believing there's a third row. Sorry, in between the. Sorry, we've got the yes, A and B is of course a conclusion. Sorry, there's a third fact. Sorry, there's a second premise.
I understand. You want to add another column because
of something else that we're already with.
Case, there could be some other cause, and that's why B is true. I get that. But now,
and that's what, and therefore that's why this makes sense. This A implies.
I know, but make it make sense for the fourth row.
Oh, I see. Well, that means that something else has to also be false, whatever it is that could be the cause. and therefore all three of them are then the rains are falling, and the other cause can't be there, and therefore to make that true, I'll have to think about that together completely.
Yeah, so I mean, I totally get what you're saying. It could be some other cause, and that does make sense out of this third row here, right?
Yeah, so why would you call that true?
But trying to stick with there could be some other cause falls apart for me, at least, with the fourth row. But before we go on, Alex, that's why I did my Trump thing, right? So I think it's cheating. I had a feeling that there was more to this, right? But that's why I want to stand by my Trump analogy, that this is a way to sort of make sense out of the outcomes that we are by convention forced to agree with, right? So.
Oh well, hold on. Don't forget, when we say that this thing is true, the thing on the right-hand column, we're saying that relationship is true. That's what that means. That in the column, that's saying whether or not the relationship between the A, which we're saying is if it rains, and B, it is wet.
Yeah.
That column is saying whether or not that relationship is true, and so the two false is still saying yes, that relationship is still true. You can have it as false in A, and the result being false. Therefore, the relationship is still true.
Yeah. So I think what you're like latching onto is a reading of if A then B, like, because your example is given it in terms of causal relations between the antecedent and the consequent, which are much stronger, or at least much more fine-grained than what we've got on offer here. So the material conditional is not a good representation of causal relations between things.
But that's what it's used for, though, isn't it? Quite often.
Well, it would be always used poorly if the material conditional is, by which I mean this conditional that we're looking at now. This is the definition of this conditional.
Yeah.
If that was used,
I agree with
your
Rumpel.
example shows you.
That's the only way we use it in real life. We really do mean to imply cause.
Well, there's a good case to be made for saying that that this material conditional doesn't really have an English language correspondent. But anyway, I will consider a couple of different candidates in this series of slides. There's quite a lot of content, so if we don't mind, hopefully I'll gloss at least something close to what you were saying anyway. So let's and then if nothing in here is what you wanted to say, then you can make a video to explain what you wanted to say anyway. Because I'm got maybe 20-25 minutes before I'm going to have to go.
Oh great, yeah. Sorry, I didn't mean to hold you up, Alex. Sorry, I thought you were inviting comment here. I didn't realise. Yes, I didn't want to.
Well, I'm quite happy for there to be comments. I'd rather get through all of this.
Yeah. I'll shut up.
All right, good. So, right. So we've got the first row and the second row are all right. I think everyone's all roughly okay with it. Like if A then B, if it's true that A and it's true that B, then if A then B is true. And similarly, if we're saying if A then B, but A holds and B doesn't, then if A then B doesn't hold. That makes sense, I guess. But then the question is, like, what do we make out of the other two? Because they're the ones where most of the problems come in. Well, what we could do to try and change things, because before they're both true, we could try making them both false. And if we do that, then it just is the truth table for and. Right? So then there would be no point in it. It would be redundant. We could try making that one true, the bottom one true, and the third one false. And then it's just the truth table for biconditional, so it would be redundant again. If we try making them third true and fourth false instead of having them both true, then what happens is if false then true implies that if A then B is true, so if we're saying if it's raining then it's wet, and it's false that it's raining, but it's true that it's wet, then it's true to say that if it's raining then it's wet. It just doesn't really help in any way. It's like the problem with it isn't that it's the wrong truth value, it's that there doesn't really seem to be any truth value that makes sense with this combination, I think. Anyway, let's look in more detail at exactly how weird this gets, right? And it's mainly because of the third line that people talk about the paradoxes of material conditional. They give you both weird results in terms of truth and weird results in terms of validity. Right, so some things which we don't think should be true, it says are true, and some arguments which we don't think are valid, it says are valid. Like by don't think are true or don't think are valid, I mean in everyday speech and stuff. These are the sorts of things I think that maybe Rumpus was getting at. That it's the third row really that makes it go wrong, I think. So you can have a formula like this: if I'm dead, then I'm alive, because it's true that I'm alive. The first bit, if I'm dead. Well, that's, well, at least this proposition, I am dead, that's false. And this proposition, I am alive, that's true. So it's if false, then true. Well, on the material conditional, that comes out as true. So material conditional sense of if then says, if I'm dead, then I'm alive, is true. Right? But it sounds like a contradiction. Right? If I rolled an even number, then I rolled a 1. Because if it's true that I rolled a 1, then if something false, like I rolled an even number, then something true. That this conditional is true, but saying if I rolled an even number, then I rolled a 1 sounds like a contradiction. It's not so much that it's just unintuitive or something; it's just downright wrong. It's about as wrong as anything could be. So these are the things that people talk about as paradoxical formulas. Okay, good. So I've just spelled it out in more detail. Great.
Yes, I must admit, my example wouldn't fix that.
Right.
Great way, because they're actually the same thing that you're.
Right, and so here's another way we can have arguments. So this was individual formulas going wrong that come out with saying that this formula is true, and in actual fact, it sounds like it's not just false, but it sounds like a contradiction. Here's a way that an argument can come out sounding valid, or an argument which shouldn't be valid, but comes out as being valid because of the way that we've defined the material conditional. So here's P, therefore if Q, then P. It's valid. Right, here's a tree that closes. Here's a truth table showing that there's no row where the premises are true and the conclusion is false. Or, sorry, that's not right. Here's the tree that closes, and here's the 2 rows of the truth table that correspond to this branch. Anyway, the argument's valid. If P, therefore if Q, then P. But that's just like this. I am alive, therefore if I'm dead, then I'm alive. Right? That's an argument which is valid. Now, it seems like it shouldn't be valid, but it's valid because of the definition of the material conditional. Right. Here's this one, P, therefore if not P, then Q. I am alive, therefore, if I'm not alive, then Yeovil Town will win the Champions League. It's true that I'm alive, obviously. It's false that I'm not alive. For anyone who doesn't know who Yeovil Town are, they're not a team that are in any sense going to win the Champions League. Right? So it's false that Yeovil Town will win the Champions League. So it's another valid argument. If P, therefore if Q, then P. Sorry, if P, therefore if not P, then Q is valid. Because of the way that if you draw a tree out for it, the tree closes. Right, and that's again just because of the properties that the material conditional has. But obviously that argument, if I'm alive, therefore if I'm not alive, then Yeovil Town will win the Champions League. I mean, maybe you can make that make sense, but it seems like it shouldn't be a valid argument. So I'm going to look at 3 different approaches to this that philosophers have given of ways that we can try and fix this. So the first one I'm going to look at is pragmatics. That's accepting the logic as it is, but doing something else, jazzing up other things about it to try and get around. So there's a difficulty which is in natural language we speak a certain way, but in logic it gives us a different result. The pragmatics answer is to say something like, there's something else going on when we speak that's not present in the logic, and that other stuff that's going on when we speak makes the difference between the logic, which has a certain behavior, and the way that we speak, which has a different one. Basically, there's nothing wrong with the logic, it's just that there's other sort of contextual elements that come in that make the difference for us. And the probability is to say the truth table for the material conditional is wrong, it should be changed. Or you say it's only correct or acceptable or assertable to say if A then B, if the probability of B given A is high. I think that's probably closer to what Rumpus was talking about a minute ago. Maybe, who knows? And then the third option, or at least we'd call them 1A and 1B, then the second option is possibility. So we just have a different logic altogether.
So I'm wanting number 2 there.
Okay. Well, I'll show you
1A and
what's
1B really suck, right?
I like all of these, but there's problems with all of them. So let's have a look at the pragmatic option first. So it's the most conservative. So we just bite the bullet and accept that the logic of the material conditional is correct. But what we do is to explain why it seems weird by talking about the other features of language use in general and conditionals in particular. So this is what this philosopher Paul Grice advocated in his cool book called Studies in the Ways of Words. So he's kind of the father of this kind of linguistic pragmatics sort of school of philosophy. I guess the point here is that you're saying mainly that, like, well, there's another reason why you wouldn't say, if I'm alive, then I'm dead. Or sorry, if I'm dead, then I'm alive. Yeah, okay, it's not like a contradiction in the logical sense, but it's not assertable. Like there's some kind of rules which mean that it's wrong to assert it, even though it's not technically false. That's the basic backbone
Did
of this
he
answer.
figure out what those are?
Oh yes. Don't worry, I'm going to give you some of these. Not all of them, but I'll give you some of them. Okay, so this conversational implicature. So here's two people talking to one another. I hear that Smith's got a job in a bank. How's he doing? And then B says, oh, quite well, I think. He likes his colleagues, and he hasn't gone to prison yet. Right? There's something weird about this. It's not that it's made a logical mistake, but there's some kind of like rule of conversation which has been violated by B's answer to A's question. Right? It's the last bit. Like, how's he doing? Oh, he's doing okay. That's basically what it means. Is he enjoying his job? Is he getting on well or something? You're not asking how's he doing in the sense of like, has he gone to prison yet? Right? That's just not on the radar of the question that A is asking. So there's something, B is asking something which wasn't implied by the question. Here's another example. I don't think that Smith has a girlfriend these days, and B says he has been paying a lot of visits to New York recently. Well, in this, B's implication, in the sense that he's saying he's been paying a lot of visits to New York recently, is to say that he does think that these are actually Grice's examples. So I would have probably not come up with these ones. They're not necessarily the clearest. But I think B's response to A is saying here that he does have a girlfriend because that's why he's going to New York. And so there's he's implying something about his answer, which isn't the same as the kind of implication that we've got with the material conditional. So I suppose what these two examples are showing you is that, like, in ordinary conversation, there's that there are kind of rules which we can go wrong with by thinking that somebody is implying something when they're not, or there's a sense in which we can go wrong by implying something without directly stating it. Right? That B's reply to A in the second instance doesn't say, well, he does have a girlfriend, he's gone to see her in New York. He's just implying that without stating it. So he's like implying more than he should do. And in the first case, he's taken an implication from A's question that isn't really there. Anyway, right, in the previous cases, right, so B's responses are not false, but they implied something other than what was said. Right, so here's the first of Grice's principles, the cooperative principles. Make your conversational contribution such as required at the stage at which it occurs by the accepted purpose or direction of the talk exchange in which you are engaged. So don't say more than you should do. Right, so this isn't a logical rule. This is kind of like a conversational rule. or a way of engaging with one another that you could fall foul of without saying something false or implying a conclusion that wasn't implied by the argument that you were making. So what we were talking about really formal rules previously, these are not formal rules, they're like really informal rules. So he kind of catalogues a load of these. So main categories being quantity, quality, relation, manner. So in the quantity, breaks down into 2 subsections. So make your contribution as informative as required, and don't make your contribution more informative than required. In the quality section, try to make it one that's true, so that you don't say stuff you believe to be false, and don't say that for which you lack adequate evidence. Be relevant, be perspicuous, so avoid obscurity, avoid ambiguity, be brief, blah, blah, blah. This is a very long list, so I'm just giving you like the initial beginnings. So I'm only going to say what's relevant to our. Then don't worry, I will wheel back a little bit to our material conditional problem. Let's have a look just a little bit about it, because I really liked these when I was researching it, so I've gone into a bit of detail about the first couple. So let's look at quantity. What does he mean by make your contribution as informative as required? So here's a way of going wrong. A says, are you going to the pub tonight? And B says, either I will or I won't. Technically speaking, he hasn't violated a logical law. What he said is true. Either I will or I won't. But it's inappropriate, doesn't help A. It's not as informative as required. It's less informative than required. Don't make your contribution more informative than required. Are you going to the pub tonight? I will, and David Cameron is the Prime Minister. Right, again, technically it's true. I will is all that was required. And tagging on any other true thing results in still a true, true and true means A and B is true. Technically B's response there is true. So tagging on and David Cameron as the Prime Minister doesn't change the truth value. So there's no logical problem with that, but it's inappropriate again. Right? It's just, I'm not asking whether David Cameron's the Prime Minister, I'm asking you if you're going to the pub tonight. So there's ways that you can go wrong in answering this that aren't logical ways that you can go wrong. It's kind of informal rules of conversation. And quality, right? Quality part A saying don't say what you believe to be false. So here's deliberately breaking the rule, which is he thinks this is what irony, metaphor, and this thing he called meiosis is. So irony, I could say something I deliberately believe to be false, which is that Dirty Dancing is my favorite musical ever. Right? It's not, in case you're wondering. So that's me being ironic, is saying something that I believe to be false. And irony is one of these things that everyone gets it wrong. All irony means is saying something that you think is false. If we look it up in the dictionary, that's all that it means. So Grice's characterization of it as breaking the part 2A of everybody's implicit contract of conversational relevance is what irony is. Again, saying metaphors, saying stuff that you deliberately believe to be false. So when I say you are the apple of my eye, I don't actually mean you are the apple of my eye, right? But the essence of metaphor is in a certain sense, in a slightly more permitted sense, but saying something that you believe to be false, right? And so meiosis, it means sort of like understatement or something. If you say Hendrix was a little bit good at the guitar, that's false. You know that he's actually really good at the guitar, but you underplay what you're saying to have a certain effect. So it's not like logic would just say that all three of those, irony, metaphor, meiosis, just false, 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 next kind of thing. It doesn't have the resources to be able to see what you're doing by saying something false. And sometimes you're doing it, to make a joke, or to, compliment someone in a poetic way, or to, deliberately understate something in order to make the effect, right? When you're saying we're a little bit good at the guitar, I think everyone knows what you mean in a certain context when you say that. Anyway, so also don't say that for which you lack adequate evidence, which is an internet rule that should be followed more. So yeah, so someone could say to someone else, yeah, she's probably cheating on him, and all that they mean by that is that they just don't like her. It's kind of like sometimes I guess it could be like the essence of bitchiness or something. It'd be like deliberately saying that for which you lack adequate evidence, just spreading rumors or that type of thing. So
sounds like the Republican debates.
Yes, right, exactly. There's all sorts of public that's why Grice is great, because you can really apply this to everyday life in a really easy and like fun, illuminating way. I'd recommend this to anybody who wants to follow them. Anyway, let's just plow through this, because yeah, I can hear my dinner's being made already. Anyway, so yeah, 3, be relevant. So here's deliberately breaking the rule. This is the not being relevant exchange. So this is at a posh tea party, and A says, "You do have a lovely house," and B says, "Thank you," and then A says, "Oh, that Mrs. Jones is a stupid old windbag, isn't she?" And then everyone has a shocked pause, and then B replies, "The weather is lovely today." Right now, B is the one making the mistake here, although it sounds like A is. But B's response, the final thing, isn't relevant to what A said. But it's on purpose, because it's the deviation from the rule of being relevant, which is to bring the conversation back to where it's supposed to be, where the rules of that posh environment are allowing it to be. You're not allowed to say that Mrs. Jones is a stupid old windbag in the posh tea room, right? And by A bringing it back, he's giving a signal. Sorry, by B bringing it back, he's giving a signal, like kicking A under the table, telling him to shut up. It's really obvious that he's like ignoring what A says and saying something that's not relevant. So sometimes breaking this rule of relevance is like, I mean, this maybe doesn't translate into America, I don't know, but it certainly is in the UK. That, you know, it's like if you're in one of these formal situations and you say something and then everybody ignores it and starts talking about something else, that means you've said something wrong. Like if someone's deliberately breaking the relevance rule, that means that, you know, they're telling you something. Anyway, so be perspicuous. This breaks down into 3 things again. Avoid obscurity of expression, avoid ambiguity, and be brief. So obscurity of expression. In the presence of a small child, you might not want to know what you're talking about. You might say, I wish to asseverate my propitiation with last night's coition. Coition? Coition? I'm not even sure how. It's coitus, isn't it? But is it coition? Anyway, so I don't even know. I found these in synonym generators. But you might say, "Oh, I wish to asseverate my propitiation at last night's coition," to your partner, to mean I really enjoyed sex last night, just so that the small child doesn't pick up on what you're talking about. So there might be situations in which you can deliberately break the avoid obscurity of expression rule, but to do so, you have to have some kind of overriding purpose. In everyday conversation, breaking the rule like this would be a faux pas or something. Avoiding ambiguity. So, right, yeah. So there's this general who captured a guy called Sinned, and he sent a message back from the front line which says, "I have sinned," and it was translated meaning that he has like sinned as in the religious thing, rather than that he has sinned as in the person sinned. So obviously, saying stuff that's ambiguous, it's really easy to see why that's wrong, because it's breaking the rule of like not saying stuff that's unambiguous, right? Someone could misunderstand what you're saying if you say that. Also, being brief. Johnny failed to produce a series of sounds which adequately followed the accompanying music might mean Johnny's singing was terrible. Just say it as Johnny's singing was terrible. Why say it to a long-winded way of saying it? So there's all these like ways that you can go wrong, like failures, breakdowns in language, which are not logical breakdowns and failures in language. That's basically what all of them, I'm going to be hammering home with loads of examples of there's things that you can do wrong that don't correspond to logical mistakes in any way. Does that make sense?
Yeah, that's all very good stuff. Yeah, very
okay,
funny.
great. So
I think it's propitiation, by the way.
Is it? Okay, good. Anyway, so here's how it applies to conditionals, right? So you say, "Are you going to the pub tonight?" And then B says, "Well, if the third moon of Saturn is made of cheese, then I'm going to the pub tonight," right? Technically true, but it violates 3 and 4A.3. So what was 3? Let's go back. 3 was relation, be relevant. Okay, great. So it avoids 3. The cheesiness of the third moon of Saturn has nothing to do with your going to the pub. So it's violating the Gricean rule of be relevant. It isn't relevant. It's true, technically, you haven't made a logical mistake, but the reason we all react like, "Oh, that's not right," Grice is saying, is because it's violating these conversational implicatures. We're not supposed to be saying this. It's going wrong, not in a logical way, but in another way, in this way. It also violates 3.A because there's a more brief way of saying it. Are you going to the pub tonight? Or if the third moon of Saturn is made of cheese and I'm going to the pub tonight, you could just say I am going to the pub tonight, right? So you're violating the saying stuff that's irrelevant and violating the I could say this much easier. Both of those two rules are going wrong, and his answer is, why is it that the everyday English sense of if-then seems different to the logical one? Well, his answer is the logical one's just stripped away all of these non-logical conversational implicatures that go around it. Like there's no pragmatics with logic. And once you pile in all of the pragmatics and look at the behavior of implication, then it's like what we thought it was like. If you strip all of those away, it's just what the material conditional says. So that's his answer. It's like you don't need to change the logic. You just need to realize that when you're using the if-then, you've got all of these other things going on in the background which are not logical, strictly speaking. Okay, cool. Let's plow on.
Yes, very illuminating. Yes.
Good. So I guess here's another one, right? A says, I am going to the pub tonight, therefore if I'm not going to the pub tonight, then the third moon of Saturn is made of cheese. Technically it's valid, but it violates 3 again because it's got nothing to do with the cheesiness. Going to the pub has nothing to do with the cheesiness of the third moon. So it's exactly the same thing, just in relation to arguments, right? So the Grice's diagnosis applies just as well, not just to the truth case, but also to the argument case of where the material conditional seems to go wrong. Okay, great. So there are problems for Grice's theory, though, right? So some conditionals seem to get the wrong answer. So it won't rain, but if it does, we'll hold the party indoors. Well, that seems to violate 4C because it would be briefer to say it won't rain. Perhaps it also violates 3 because given that it won't rain, it's irrelevant to speak of what would be the case if it will rain, possibly. But it seems like we should find that conditional weird because it's violating the rules that the other ones seem to do. But we don't find that one weird. That one sounds fine. So Grice's diagnosis said, oh, all those paradoxes of material implication, well, they just sound weird because they're violating these rules. And then the counterexample is, well, here's something that seems to violate your rules that doesn't sound weird. So violating those rules can't be the explanation of why those material conditionals sounded weird. So before we all go away thinking that Grice solved this, there probably is more to it than what he's saying. Not that this is a knockdown argument, but, you know, there must be other stuff going on because it doesn't explain this case properly. Okay, so here's the probability explanation onto the second one. So Frank Jackson is this Australian philosopher in this book called On Assertion and Indicative Conditionals. Says a statement of the form if P then Q is more assertable the higher the probability that Q is true on the assumption that P is true. So this if A then B is assertable if and only if the probability of B given A is high. So premises and conclusion is assertable if the probability of the premise is lower than or equal to the probability of the conclusion. So the premises don't lower the probability of the conclusion. They are, in fact, themselves lower than the probability of the conclusion. That's his answer. So what does that mean in particular? You say, if I rolled an even number, then I rolled a 1. Right? I rolled an even number is false. It's true that I rolled a 1. Well, that comes out as true. It is logically true, but for Jackson, the probability that I rolled a 1, given the fact that I rolled an even number, is actually 0. And what he's saying is it's assertable if the probability of the antecedent given the consequent is high. The probability of the antecedent given the consequent is 0 in this case. So while it's true, it's not assertable. Assertable meaning something like you shouldn't say it. Right? It might technically be logically true, but it's like saying something like I don't believe that I exist, or something. It's like it's not really assertable. It doesn't really mean something correct to say that. You have to believe that you exist, and in the same sense, he's saying you can't assert properly. If I rolled an even number, then I rolled a 1, and this is why, because the probability of rolling an even number, given that you rolled a 1, is 0, or at least not high. And then this works with the arguments as well. If an argument is valid if the premises can't be true and the conclusion false, an argument is assertable if and only if there cannot be a probable premise with an improbable conclusion. Probable premises with improbable conclusions. So the argument above is valid. However, it's only the premise is only somewhat probable, and the conclusion highly improbable. So you can't have probable premises with improbable conclusions. The probability of the premises is much higher than the probability of the conclusion, and that means it's not assertable. You can't say this type of argument. Even though there's nothing logically wrong with it, it fails this probability test, and that means that you shouldn't say it. It's not an assertable thing. Okay, so there's problems with this. If it's reasonable to talk of material conditions being conditional probabilities, which is probability of A given B, then it must make sense to give unconditional probabilities to A and B as well. So if the probability of A is n, where n is somewhere between 0 and 1, let's just say the probability of A is somewhere between, in this, it's going to be somewhere in between 0 and 1.
Yeah.
But presumably you want to say that the probability of not A is just 1 minus the probability of A. And that makes sense, right? And so the probability of A plus the probability of not A is 1. And that means that the probability of A or not A is 1.
Yeah.
Right? That all seems perfectly straightforward. There's nothing to object to here at all. But this is going to backfire, right? So you want to say that A or not A has a probability of 1 because A or not A is a tautology. And in classical probability theory, all tautologies get given the probability of 1, which is what we just sort of showed a minute ago. But then the probability of if P, then if Q, then P, well, because it's a tautology, then it should get given the probability of 1. But then if you plug stuff into that, you can just, because tautology, you can say if I'm alive, then if I'm dead, then I'm alive. That's an instance of if P, then if Q, then P. So then it gets given a probability 1 because it's tautology, and thus it's assertable. Right? So Jackson's theory, again, while it gives a reasonable diagnosis to something, when you first think about it, this does seem to capture something about why it's wrong to say this, right? Because there is something about the probability. There's a relation between the probability of the first thing and the second thing, and it gets that wrong, and that's why you shouldn't say it, right? That seemed to me something similar to what Rumpus was saying a minute ago. But then again, these are just giving these very, very simple, straightforward. You can't object to any of these assumptions, and it just gets you that you just realise that it's not going to do the job that you want it to do. It might be explaining something that's gone wrong there, but it's not the full story of what's gone wrong there. Because if it was, then it wouldn't. You wouldn't get that if I'm alive, then if I'm dead, then I'm alive as probability 1 and assertable, right? So we managed to get. We managed to say that if I'm alive, therefore if I'm dead, then I'm alive, and we managed to say that was unassertable because of the probability considerations we just had a minute ago. But then the same considerations about probability end up saying that if I'm alive, then if I'm dead, then I'm alive, is assertable, highly assertable, because it's got a probability of 1. So that means that this diagnosis is not necessarily much of an improvement if we're still, it's a gate that's supposed to filter out all of the paradoxical things, and it lets through some really shockingly paradoxical things like this, then it's not a very good gate that's filtering out those paradoxical things. So let's look at one more. So this is a guy called C.I. Lewis, who was a logician from the beginning of the 20th century, American logician, who essentially came up with a type of logic called modal logic. He was kind of the pioneer of this. And he was motivated by the paradoxes of material conditional. He read Bertrand Russell's Principia Mathematica and discovered this material conditional and really didn't like it. And so he set about more or less his life's work to come up with a different way of thinking about the conditional. So he came up with this thing, called it the strict conditional. He gave it this symbol instead, called the fish hook. And he said it was stronger than the material conditional, and it's supposed to capture the way in which proper conditionals work, and not the way that the material conditional works. So if in material conditional, if A then B is true, if and only if, as in it's equivalent to not A and not B. But Lewis's idea is that A strongly or strictly implies B is true if and only if it's not possible that A is true and B is false. Right? It's not just that it happens to not be the case that A is true and B is false. Not just that it happens to be, but it could be any other thing. It says it's not possible that A is true and B is false. Now, you can't really capture this notion in the propositional logic that we've had so far. We're reaching now beyond the resources that we had when we're talking about not possible. This is why we have to actually add to the logic and change it in some way. So what we do to make this is we're extending propositional logic, technically speaking. So we say that to say that a proposition is possible, we add a new symbol, which is this diamond symbol. It's a monadic symbol like negation. So it's if. So we're adding a new grammatical rule, which says that if A is a formula, then diamond A is a formula. So if A, then possibly A is a formula. And given A, given diamond, then we can define not a sense of necessarily in terms of this. So there should be a box in front. There should be a box here. Imagine there was a box there. I don't know why it's not there. But box P just means not diamond, not P. And that's saying necessarily P means not possible that not P. Right? Something's necessary if it's not impossible.
Right.
Sorry, it's necessary if it's not possible that not P.
Yes.
Right?
That's better,
so
yes.
Now if we've got one new symbol to mean possibility, or possibly, and we can just define another one, box meaning necessarily, we can say more things in the propositional logic than we could do before. So the material conditional has this equivalence: if A then B is equivalent to not A and not B. Well, Lewis's idea was that the strict conditional has a similar definition or equivalence. So A strictly implies B means that it's not possible that A is true and not B is true. It's not possible that A is true and B is false. It's not just that A isn't true and B is false. It's that it's not possible that A is true and B is false. I'm being told I need to hurry up, so I will. Right, so let's just chuck it in and see if it solves the problem. So we say if I rolled an even number, then I rolled a 1, right? So if P, then Q. That's true because I rolled an even number, but not a 1, right? Is that right? I don't even think that's right. What am I talking about? If P then Q is true because I rolled an even number but not a 1, that means that this is true, but that's false. I must have written that wrong. It's true because I rolled a 1 but not an even number, I think that's supposed to say. Not bollocks.
Needs a box in front of it.
Yeah. This. Oh, damn it. You know what? So I've written these round the wrong way, but everything else works. Essentially, the idea is supposed to be if. So if P then Q, in the case where P is false but Q is true, right? That still comes out as true on the material conditional. It's the third row of the material conditional, the one that we all found strange.
Yeah.
And then Lewis's line is, well, no, P strictly implies Q only if it's not possible that that P is true and Q is false. So it's not possible that. So in this case where I rolled if I rolled an even number, then I rolled a 1, because it's not possible that I rolled an even number and rolled a 1, then this if P then Q comes out false. Right? Because it is possible that I rolled an even number and not a 1, then it would come out as being if P then Q is true. Does that make sense? It doesn't make sense really, does it? I really should.
The last sentence makes sense.
Well, we don't want to keep you from your dinner, Alex. Don't get into trouble.
Yeah,
well,
I think I agree with that.
Why don't I start off next week by picking up at the beginning of this possibility, because I could do a much better job with this, and I'm confusing myself both by being half out of the room and the fact that I've actually written a bit of the slide wrong. But I could certainly explain this a lot better.
I would love that.
Things
We'll start next time with the Lewis stuff.
Okay, good. So let's just quickly say, so we've done propositional logic, we've done the trees, we've shown how to show that an argument's invalid with trees and if an argument's valid with trees. We've shown the relation between trees and truth tables, and we looked at soundness and completeness. So we've done quite a lot tonight already, and we've done all this stuff. But yeah, okay, next week, possibly a little bit later, possibly starting at 6 next week, we'll carry on with me explaining properly the stuff about modal logic in a much better and more confident manner.
That sounds wonderful. Thank you so much.
Okay, all good. No trouble.
Have a great dinner.
All right, thanks very much. See you later.
Thanks, Alex. Bye.
Cheers. Bye-bye.